Okay, it's recording. And first of all, any questions you'd like me to address? Yes?
I was hoping we could go over the Kim Tucker.
Okay.
Not the whole thing, but can we go over
Like the problem?
The constraint, yeah, the set, because it has the.
Okay, so I was going to start 4.2.
Okay.
Okay, so that's fine. So I meant any questions from the material, from its chapters or anything like that. If there is any, might as well address it now. No, okay, so let's say a few things about, okay, 4.2 is your first problem, right? So that wants the contacker for cost minimization. So let's remember what the setup of the problem is. So you have to minimize. Do we have, yeah, okay, so we have many. So let's set it up this way. The sum for I1 to n of this by choice of the xi variables. I could have written it in a vector form. Maybe it's a little easier if I write it like that. It's of course the same thing. Now, what are the constraints? And by the way, I don't like to try to remember two different things, and especially since the second order conditions for a minimization and maximization problem are different. So what I'm going to do instead of that is I'm going to do max with a choice of the same variables from I1 to n minus the sum. Right, so if I maximize minus this amount, then I minimize the amount, right? So that's at least my attempt to conserve just how much memory I need to devote to remembering theorems. Believe it or not, I'm up to the max. So we're going to do that. Now, the important thing is to write all the constraints as they appear in the economic problem. Now, in the economic problem, what are the economic assumptions we make? The x's are factors of production. It doesn't make sense for them to be negative, right? If we write it like that, if we write it as a y, then by convention, the components of the y vector that are inputs, net inputs, are written as negative numbers. But the moment you have this, the x's are non-negative, right? He's been consistent on notation on that score. So the constraints are the non-negativity plus one more. So I'll write that one first. So subject to f of x1 dot xn greater than or equal to y, because you need to be able to achieve a certain level of production, y. And for every I, xi is greater than or equal to 0. Right? So, all right, what do we do when we have problems like that? There are two ways to approach this one. One is to just include this constraint explicitly, and then write the first order conditions where the derivatives with respect to each xi are less than or equal to 0. Okay? And then the complementary slackness. Since I introduced in my own note that I wrote over last weekend, I introduced a multiplier for everything to really explain why we do this weak inequality. I am going to do it. I'm going to do it this way. Your answer can be whichever you like. So I'm going to first write the Lagrangian, but you see, I needed to decide if I'm including these explicitly in the Lagrangian before I can write it. So I'm going to also decide on names for the multipliers. How about I call lambda the multiplier for this constraint, and for each one of these, I'll use the next Greek letter mu, because it's nice to start at, I1 and so on. Another solution would be to write this lambda 0 and then lambda 1, blah, 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 whatever you like, it doesn't matter. In fact, I looked at his answer key, and he calls this multiplier t for some reason. Okay, so I have then the Lagrange function, which is a function of lambda, the mu's, and the x's. And that function is, well, you take the objective, which is minus this sum, and then you have the constraints. So my preference is always to write like this, a plus, and then in here I'm going to write something that is non-negative. I believe the book, actually, let me see how he has it, because I don't want you to think I'm doing something different. Where is that? Inequality, yes. In his inequality constraints, right, what he does is he has the constraint written as less than or equal to 0. The GI is the constraint. So page 503. And then, where does he write his Lagrangian? He doesn't write his Lagrangian. It's massively annoying, but there you go. So you have all of these. Okay? Does that make sense? Yeah, question.
So if it was, suppose xi was greater than or equal to 2.
Yes.
That was our constraint. Then would it be
Then
if
it, let's say x1 is greater than or equal to 2, then here,
it would be minus 2.
yes.
Okay.
Yeah, exactly.
I just understood.
The convention is when you're going to deal with inequality constraints, you will have plus the lambda multiplied by the constraint written in such a way as to make it non-negative. Okay? A lot of the books I know, Zusai likes to write it with minus lambda, and then the constraint is non-positive. So you would have to flip it. But it's, of course, mathematically the same exact thing, right?
Yeah.
So I'm getting old, so I'm going to stick to my conventions that worked well for me since I have first learned this technique. All right? You would also quickly... wait a minute.
Yeah, I gave them 0 actually, but I don't know. I gave them 0 out of 20 because you were there.
Wow. Then it's gonna make it look a little funny because I'm maximizing the negative. So when I take derivatives here, I'm gonna get a negative WI, and then, yeah, that's fine. That's fine. Let's write them down and we'll see. All right? So, let's take the derivatives with respect to every choice variable.
Can I ask one question?
Yeah.
Suppose that just we did it from the minimum and we didn't do the negative. How
Right.
would our Lagrange look? It would be
It will have you will have to put negatives here.
like what we just talked about.
Yeah.
Okay.
So it's essentially the same thing, just
Yeah,
flipped
just
around.
curious.
Okay?
Okay.
Okay. So first order conditions. You will have all the constraints, of course, have to be true, right? And at the same time, you will need to take the derivatives of the Lagrangian with respect to each of the variables. Now, because we have accommodated every constraint, including the non-negativity constraints, explicitly here, all our derivatives will be equal to 0. We will see how from that we derive the weak inequality you see in the book. Okay, so I'm going to do it for just one. So with respect to WRT xi, what is the derivative? Is it even visible? Almost not. But the other markers are going to be really hard to erase. Okay, well, oh no, this one shouldn't be. Let me see if it's too faint. So I have minus, oh, it's not, minus Wi, right, with respect to xi. And then an xi is in here, so it will be plus lambda partial of f with respect to xi, evaluated to optimum, of course, right? And then from here, plus mu I, and it needs to be equal to 0. Any questions? This will be true for all I, right? So for all I, you will have a condition just like that. But it's not the only thing, right? You need to also repeat the constraints, right? And your multipliers, the lambda and all the mu's, have to be non-negative. It's part of the theorem that they will be non-negative. So this is not the only thing I know. I know also that lambda is non-negative. I know that mu I is non-negative for all the mu i's. And what else do I know? I know that every one of my constraints must be true, right? Must be satisfied. So all of these are part of the first order conditions. You repeat the constraints explicitly. And finally, for every constraint, I shall have the complementary slackness conditions. Okay? So I'm going to write the complementary slackness conditions under each of those constraints. So for this one, it will be that lambda multiplied by the f minus y is 0. And for these, it will be that mixi is 0. Now again, what is the interpretation of the complementary slackness conditions? You interpret them best by remembering that the multiplier tells you how much your objective function will be improved if the constraint is relaxed a little bit. So each complementary slackness condition says the following. Suppose that you've decided that, let's say, one of the xi's optimally needs to be positive. This then says the corresponding multiplier simply must be 0, right? Because a positive number, to make the product 0, then mu I must be 0. So the interpretation is, if for this constraint that says xi is greater than or equal to 0, you chose to not hit the constraint, it means the constraint does not bind, does not bother you. And therefore, it's the measure of how much you're bothered by the constraint, which is literally the multiplier, should be 0. Vice versa. If the multiplier is positive, it means that you felt in your maximization that the constraint is binding, is bothering you. In which case, you've hit the constraint. You can't go any further because of the constraint. So then the xi will be 0. The same story here. If this constraint is binding, if this constraint is not binding, which will not be the case in this situation, but if it's not binding, then its lambda should be 0, right? That doesn't bother you. Now we know the objective function is strictly monotonic, so you're going to hit this constraint for sure. You're not going to ignore it. So that means then it's going to bother you. The lambda is the marginal cost, as we know, right? So that's the interpretation. These are all the first order conditions. Now, to make them look more interesting economically and to match the presentation in the chapter, we are going to take these up here and we're going to solve them with respect to mu and use this and use that. All right? So let's take one of them and write it as follows. Mu I equals Wi minus lambda partial of f with respect to xi, all at the optimal point, right? X star. Okay, and the lambda star, of course. I should have been putting stars on these all. At the optimal solution, they are a specific set of values for these variables that we get. Okay? Now, observe, if I take this and I say from here that needs to be not negative, right? Then I have this version of the constraint. If the xi is furthermore, I have this. So this can be written like that. But if you take that difference and multiply it by xi star, the product should be 0. So there you have it. That's the reason you get those Greek inequalities. And you saw a variation of that in a previous homework problem, and in the profit maximization chapter, he gives that on page 29, right? And if you look at page 29, it's almost the same thing, but here, instead of a lambda star, you have the price of output. And just to put everything together, when do we do profit maximization? When the firm is a perfect competitor, that is, a price taker in both the input and output markets. What do we know, even though we haven't covered it in this class, you know it from your undergraduate years. What do we know about equilibrium in competitive market? Price equals marginal cost, right? We tell it to principal students. But this here is the marginal cost, right? So it all comes together very nicely. Okay? So write it, bring it to this point, and explain that, you know, this inequality needs to be true, these need to be true, these have to be true at the star points. I didn't put stars, which I should, and so on. I should go through and do this everywhere. Okay, that's it. That's 4.2. Now, the next one is 4.4. Let's see how much I'm going to say about that. Yeah. I'll ask you some questions to see if you can get it started yourselves. So here we have a firm that has two production plants with different production functions, right? All right, so that's 4.4. So plant 1 has production function x1 to the a times x2 to the 1 minus a. The other one has production function x1 to the b, x2 to the 1 minus b. And the firm needs to produce a certain amount, right? And needs to decide how to distribute it. How much to produce in one plant, how much in the other. Possibly all in one plant, who knows, right? Okay, in other words, you're gonna say, okay, we have a y that needs to be produced. And if we have a y that needs to be produced, as that is waking up, let's close this door. It's fine that I don't trust it when it sleeps, however, it still continues to record. So I don't trust it for no good reason, but I like to see what's going on. Okay, so if we say that we're going to write y1 for the output of the first plant and y2 for the output of the second plant, then the total output is, obviously, y1 plus y2, right? So then the question is, what is the cost function that shall depend on W1, W2, and Y? Okay. What thoughts do you have about how to approach this? Yes?
You can tell that it's constant returns to scale from
Yes.
A and 1 minus A.
Yes, and also b by 1 minus b, so each one. So the individual cost functions of these will look like what?
They will just be as a function of the output, Y.
What sort of function of output?
Like linear?
Yes,
Yeah.
not even like. A linear
Yeah,
function.
so
Each one will be a linear function of output.
So-
You know the cost function of a Cobb-Douglas with constant returns to scale, right? So write for each one the cost function for it, right? So I'm going to not bother to write all the W1s to the A and the B and whatever that the formula involves, right? So how about I write it like this? The C1 of W1, W2, and Y1 for the first plant is going to be something, let's call it A, times Y. The A will be a function of W1 and W2, right? In fact, why don't I write that explicitly? Right? So then the other one is going to be something, let's call it a function B of W1, W2 times Y2. Right? All right. So, let's think of it this way. You're starting at 0. You're producing nothing, and you're thinking, I want to produce my first unit. Right? If I produce it in plant 1, my cost will be A, W1, W2. If I produce it in plant 2, my cost will be B of W1, W2. Where do I put it?
Smaller.
The smaller one of the two, right? So the cost, and that extends for every unit. The marginal costs here are going to be constant for each plant because they are constant returns to scale technologies, right? So that will never change for the first, whatever I said for the first unit is true for every unit subsequently. Make sense? So therefore, the final conclusion, and here is where I would like you in your homework to actually explain how you get this conclusion. I'm trying not to tell you everything. It's not very useful for you. You need to actually do some work in the homework. The minimum of A and B times Y is your cost function. You will just use the plant that has the lower cost per unit, marginal cost. In this case, marginal and average costs are the same, of course. So if you want to say I'm going to use the plant that has the lower average cost, that's fine also, because of the constant returns. Okay? If we didn't have constant returns, you would still have cost functions for the individual plants, right? And then you would have to somehow minimize this given the constraint, minimize the cost, W1 times X1 plus X2, okay? Plus W2 times Y1 and Y2. All right. Let me just write a few things. These do not belong to the answer to this problem because here we have constant returns to scale. So it makes it really simple. You just take the minimum and it will be the same minimum throughout the scale. So no matter how much you make. If you didn't have that, so suppose you had A, B, C, D, and A plus B was less than 1, and C plus D was less than 1. Decreasing returns to scale, right? What would be your problem then? You would minimize W1 times, now you would need some extra notation to know which amount of input goes to one plant and which goes to the other. And so since I already have 1 and 2, how about I call the plants A and B so I'm not getting confused? So then this is what you want to minimize, right? Yes? So you minimize it by choice of X1A, X1B, X2A, and X2B. And the constraints are obviously non-negativity constraints, but also subject to that the total production you make is not less than what you want to make, the Y, the total Y. So subject to X1 right? And there you have it. You would have to solve this problem. Right? In the case we have constant returns to scale, essentially you're always operating on a boundary solution. Except if the functions, production functions are exactly the same, in which case it also doesn't make a difference. You could still operate only in one plant because then there wouldn't be any difference at all between the plants. Notice the assumptions implicit in both versions, the 4.4 as in the chapter and the story I gave you here. Some assumptions that are implicit. The input prices are exactly the same for both production plants, right? And there is no differential transportation cost for the product from one plant or the other. Okay? Or you could say you've incorporated that because transportation cost is somewhere in the inputs. Questions? All right, so what's the next one? 4.6. Now, for that one, he is being very nice that he, instead of letting you derive the cost functions from a production function each, he tells you, here's your two plants, and here are the cost functions for each one plant separately, right? What problem would you set up? Given what I just showed you, it should be fairly obvious, so let me ask you, somebody tell me, for 4.6, what is my problem?
It would be
Uh-huh.
W times W1 times 4 times.
Let's see.
You just like add the two cost functions.
Yes.
Yeah.
In this case, since he doesn't give me even a notation for the x's, he already has found the cost functions for me, right? So all I want is to minimize what?
4 squared y1 plus 2 squared y2.
And by choice of y1 and y2, right?
Mm-hmm.
Subject to what?
That they must be greater than or equal to total y.
What must be greater than or equal to total y?
y1 plus y2.
Correct. And,
Wait, y, right?
ooh, sorry. Thank you. I was already mentally gearing up to write the non-negativity condition, so I screwed up. Okay? So once you realize this is the setup of this problem, doing the actual math for this is pretty trivial, actually. Okay? Any questions?
Someone wanted me to ask why Varian chooses to just exclude W. Like he writes the cost function just in terms of y here.
Because he wants you to see the bare bones of the problem.
Okay.
He's actually making it easier.
Yeah.
But he's exposing the following question for you, the students, to answer. Do you understand what really is the fundamental here? The fundamental is you have a sum of two different costs, and your constraint really looks like this. Beyond that, he doesn't want you to futz with W1 and W2 and so on.
Okay.
You could, and in fact, I'm trying to remember, but maybe one of my practice problems is like that, where the inputs are explicitly in. But I do remember I gave you one where there are multiple plants. So this is the kind of thing you want to have in mind. So this is the introductory level question. That's why he gives it to you without the W's and the X's. Right? He's already solved out for the individual cost functions. 4.8, it was for the PhD students. But, how would you go about it? You might want to try it for bonus. A firm has a production function, y equals x1 times x2, right? And if the minimum's cost of production, when it happens to be that W1 and W2 are 1, if that cost is equal to 4, then what is y? So the question is, how would you even start? Once you start, I think it's so easy that you should really try it. So, what do you think?
Do you just
Mm-hmm.
4 is your new constraint?
Well, the constraint involves the y, correct?
Yeah.
So that he's asking you to find the y. He's telling you, however, that the cost of production at the minimum when the prices are equal to 1 happens to be 4.
So it'd just be x1 plus x2 equals 4.
Yes. And also, but is that is the solution. Those x's, where would they come from?
You come from y.
Mm-hmm. So
Yeah.
how? What is the write down the problem? Minimize x1 plus x2,
Such
right?
that
Such that
x1, x2.
x2 and x2 greater than or equal to y, right? Solve this problem. It's actually quite easy. Find an expression of x1 and x2 for w1, w2, and y. Put w1, oh no, w1 and w2 is already 1. Forget that, right? So express x1 and x2 in terms of y, right? Take it from there. I'm not telling you everything. Once again, what is the crucial part of doing one of his homework problems, which is what I like about this book? If you don't set it up right, economically speaking, you're going to go nowhere. If you do set it up right and occasionally recognize that the duality identity might be handy, then, then you have no problems, you do the whole thing. All right, chapter 5, problems. So the first is 5.2. Okay, so 5.2 is very similar to one we just did. Right? Oh, wait. The one we just did might have been a little trickier and I forgot to tell you. So let me tell you which one I'm talking about. The one with the square root of y, which one was it?
4.6.
Yeah. Mm-hmm. So 4.6, back to 4.6. I said just do the minimization, right? Be very, very careful. You are minimizing a function that is concave, right? Cost functions from decreasing returns to scale should be convex. In output, not in prices of inputs, in output. Why is that? If you have decreasing returns to scale, right? Every additional unit of input you put in, for all of the inputs, if you increase by 1%, it's going to increase output by less than 1%. So it costs more and more to get a given increment of output. So the cost function should be convex in terms of output. Yes? Aha! So, if you minimize a convex function, be really careful about the first order condition and the second order condition. Is the tangency what you want? Or will you be at a corner solution of 4.6? That's the red alert I should have given you earlier. So, beware. And I see it now because in 5.2, my cost functions are nicely convex, right? And so for those, my sufficient second order conditions will be immediately okay at where you expect them to be at the tangency, at the first order conditions. Okay? So that's what I'm saying about 5.2. It's pretty much 4.6, but with better behaved cost functions for that. Okay, the next one is 5.4. Yeah. This one, I'll give you just a little bit of a beginning. Mostly because we've seen this picture before in possibly our very first homework. We had the utility function with this exact picture, right? So you will have 2, 1, 1, 2. You attempt to write your input requirement set, right? So this is the input requirement set to produce 1 unit of output. Okay? And then you think through this in terms of slopes of the isocost, right? For example, if your ratio of prices W1, W2 is so that this is the slope of the isocost, then you will have this corner solution, right? If it's in between these slopes, then you will be at this point, and so on and so on and so on. So just do it from that. Be really, really careful when you write the slopes and the relationships of slopes to remember that we have a negative in each one of those slopes, okay? And then have the intuition to double check, because this is the kind of thing that I would almost inevitably mess up in an exam, except I would then say, okay, if I have an inequality that says that W1 over W2 is less than one of those slopes, let's say 1/2, then I should be here, right? But the way it works, if you actually has the negatives, is it goes the other way around. And I'm saying that because I was reading Variant's complete answer key, and he has a mistake in that one. I won't tell you what it is. Find it. But it is a mistake of writing the wrong inequality somewhere. But intuitively, what would you say here if the good input 1 is so much cheaper than input 2, right? Then this should lead you down here where x1 is positive and x2 is 0. Right? And that's the way to verify that whatever your algebra produced makes sense. And that's all I'm saying about this one. The next one is 512 for MA students. Okay, 512. A factor of production is called inferior if the conditional demand for that factor decreases as output increases. Okay? Pretty much the same idea as an inferior good. All right? Part A, draw a diagram indicating that inferior factors are possible. And he means here, even if all our other normal assumptions we make are maintained, right? So isocost will look nice, negatively sloped, convex lines, right? Yes?
I have a tough time conceptualizing this one.
Okay.
For some reason, like I want a price to be there in order to
Yes.
understand it.
Sure. Yeah. Okay. How did we do it for inferior goods for the consumer? What sort of picture do you have in your mind? And I hope you have one. For inferior good, does it involve prices?
Yes.
Ah.
Yeah, income. Yeah.
Right.
Or
Yeah, but
yeah,
where are the optimal points? Before you know that, you have some indifference curves, right?
Mm-hmm.
Before you know the optimal points, you need to have the slopes.
Mm-hmm.
Can you do that here? Yes, you can. So draw some isocost curves. Isoquants, excuse me. Draw some isoquants, right? Choose a slope for your isocost, right? So you should have 2 isoquants, 2 tangencies, and they should be related in a certain way to each other. Okay, so in fact, this is not new. You've seen it.
Yeah.
You've seen it with a consumer.
Okay.
Part B, show that if the technology is constant returns to scale, then no factors can be inferior. Ah, okay, so how do you think you want to approach that one? Anybody else who wants to relieve Madden from answering all my questions, feel free.
I was gonna say, because your vector line would keep going out straight.
Okay, the ray from the origin will be where all the choices. Exactly, that's one way to say it, precisely. So make the argument though. Does everybody understand that? Constant returns to scale means that for any given ratio of input prices, for any y, the choice of the optimal choice of input ratios is going to be the same. It's going to be on one line from the origin, straight line from the origin, right? Along this line, when y increases, each input usage increases, right? So now you cannot have inferior factors in that case. Because if you want more y, you need to use more of every one of your factors. Part C, show that if marginal cost decreases as the price of some factor increases, then that factor must be inferior. Let's see. I'm getting the feeling I'm saying too much, so I'm trying very hard to reduce my yeah. For that one, I will tell you only that you should use the second derivative, cross-partial derivative of the cost function with respect to y and with respect to wi. Start from there. Finally, for the PhD students, 510, then you are very welcome to try it if you want. I will give you one hint. The hint is as follows. Look at the identity in the first practice problem for the second midterm. Then, take the function a supply function, which is a function of the price of output and the vector of prices of inputs, right? And find its derivative where every w changes by dwi. So it's the total differential. Find the total differential. So you need to find dy equals something, something, something. And at some point, that identity that is in the first review practice problem will come in handy. So in fact, I highly recommend the master students to try this one as another way of getting practice with that problem and seeing why that identity is useful. Any questions? All right.